So, continuing our discussion about Ito's lemma, Wiener process, generalized Wiener process. Based on that, we proceeded and found out that stock prices can be simply modeled using very simple concept of geometric Brownian motion. And continuing that, if you find out, so generally the geometric Brownian motion would consist of two terms. One is left one on the right hand side would basically be the mean drift rate, which will be given by mu, and the second term would be the volatility, which is the external noise. So, if we expand the equation in the discrete form, this is what we have. ds by s or delta s by s would basically be equal to the drift rate plus the volatility multiplied by the Wiener process, where delta s is basically spot price or stock price difference between T2 to T1, T1 to T0, T3, T1, T2 and so on and so forth. Here mu is the expected rate of return per unit time for the stock. Note, for delta small t we assume it to be constant, for other case it would be dependent on t, but in general we consider mu is not dependent on time. This is a very simplistic assumption, but if we consider the generalized Wiener process, we saw x was dependent on x and t, which is basically mu would have been dependent on s and t. That means, the mean value would depend from where the spot price is as of now and how far you will go. Sigma is the volatility of the stock. Note, for again for small delta time t, volatility is independent of time. So, again if you go back, we did consider B was dependent of S and T. If we consider this, sigma would be dependent on S and T. And also finally, we did mention, and this will stick throughout the assumption, is that the epsilon would basically have a normal distribution with 0 mean and 1 standard deviation. So, now finally, once we are able to derive, we will see that the rate of change of the stock price with respect to its present value, it would be a normal distribution, but here is what is the interesting part. This normal distribution mean and variances are not constant, they are changing with respect to time. So, the first term, which is the mu value, would be the normal value would be for the normal distribution, the expected value is mu into delta t, which is the drift rate multiplied the rate of change of time which you are considering. And in the other case, if we consider, you will basically have the variability of the volatility given by sigma square into delta t, which means that if I am able to draw the functional form of delta s into s, the mean value would change. So, the rate of change per unit time is this, and per if I basically consider a delta t time t, this is the total rate of change, total value change in the drift. And if I consider sigma square is the white noise, then for the time difference of delta t from where we are and where we want to measure the volatility, it will be given by sigma square into delta t. Now, pause, let us pause here and note. If you remember, I have been mentioning in the last class time and again few times that the volatility is dependent on time, either to a scale of delta t or to a scale of square root of delta t. Now, this is what is, if it is variance, it is dependent on delta t, hence variance could be additive. If it is basically standard deviation, it will be dependent on that function by square root of delta t, hence it is not additive. We can sample random parts for the stock market, as I was discussing, considering that the values of mu is 0.14, sigma is 0.20 and delta t is given by 0.01, whatever unit of time. So, if we find out, if you take s down, so obviously s would not be there, s would not be there. So, it will be mu into delta t, which is this, comes out to be 0.0014, and the second term was sigma into the epsilon into the square root of delta t. So, this you have multiplied by the square root, and it will be given by the case multiplied by standard deviation, the epsilon. So, what you are doing is b into dz. So, b is basically what you have is sigma into the value of epsilon into square root of t. This you know, this you know, this you generate, and you can find out. So, we have taken a sample shot at time t is equal to 0, the stock price is 20. So, I randomly sample from epsilon 0 and I take a time whatever the time 0.001, 0.11 whatever, and change in the stock price is given. So, what I do is that given this price, using this formula of mu into dt plus sigma into epsilon into square root of delta t, this you consider as constant with respect to time, this you consider constant with respect to time, find it out from the historical values. Delta t can be whatever the time difference is. Here in this case is 1 minus 0, 2 minus 1, this is just a theoretical example. So, once you are able to do that, you generate and generate from a standard normal deviate. Once you find out the change of the prices, because on the right hand side what we actually are finding out. So, this would be multiplied by s, this would be multiplied by s, this is delta s. So, once delta s is found out, this plus this would give you this, then again generate, you will get this value, this plus this would give you this, and you basically go step by step. That is 20.000 plus 0.236 would give you 20.236. Then again 20.236 plus 0.611 would give you 20.847. Again 20.847. Now, there is not a plus, because the random number generated epsilon is now negative. So, 20 plus 20.847 minus 0.329 would now give you a new value of the stock market, which is 20.158, and so on and so forth. So, these values we generate are dependent on the random sample which you generated from epsilon. So, if you are able to generate another set, obviously these values would change. So, what I meant was that if you do it a long time, infinite number of times, then the expected value of the change of x or delta x t minus delta x 0 or x t and x 0 would be 0, because whatever fluctuation you have, they would always add up to 0 in the long run. So, Ito's lemma, if you know the stochastic process followed by x, and which is the random variable, is Ito's lemma tells us that the stochastic process will be followed by some functional form of g x t. Since a derivative security is a function of the price of the underlying security in the time, Ito's lemma plays a vital role and an important role in trying to analyze the price of this derivative, which means that given the concept that they are Brownian motion, and given the Ito's lemma gives us two information, that how the rate of change of that function is happening with respect to the underlying the stock, it will give you a lot of information that how Ito's lemma can be formulated in a very simple way to find out the price of the derivative given the spot prices of the stocks are available to you. Now, consider a Taylor series expansion in a very simple one of g x t, where x is the place where you are and t is the time for that particular random variable. So, if you expand this, it is very simple. It is basically two variables. So, basically what I have, this is the first differential with respect to the first variable dx, the first differential with respect to the second variable. So, if I go to the second derivative would have basically three terms. The second derivative with respect to x twice, second derivative with respect to t twice, and second derivative with respect to x then t, and then second derivative of respect to t and then x. So, what we would be doing is this. So, if you consider the function to be symmetric, they are equal. If they are equal, they are multiplied twice, hence there is no half or two terms here. So, this is the term, and then if you consider in the cubic form, it will basically expand. So, in the cubic form, what you will have? You have delta 2 g delta z cube plus delta 2 g delta t cube, and you will take the values of x and t in these proportions. You will differentiate with x, then differentiate twice with t, or else you will differentiate with t and then differentiate twice with x, and basically have a combination of that and proceed. So, this is basically the simple multivariate Taylor series expansion. So, in ordinary calculus we have if we are able to find out, considering that we are able to ignore the third and higher terms. So, this is the first term because they are only first differential, obviously they would be second terms differential, second differential. So, now if we bring into the picture and considering that the terms of delta t as t tends to 0 can be ignored, if we go back to the slides, it will make sense. This cannot be ignored. This cannot be ignored because delta t has some value. But now consider this term. What we are doing? We are trying to find out the differential of that particular function twice with respect to t, and then multiplying by a very small term multiplied twice, which is here. So, obviously, it can be safely assumed to be 0. And also the interesting fact is that we would be differentiating the function with respect to 2 times, one with respect to delta x, which is not that small, and again if we differentiate with respect to t, that smaller value, it will now tend towards 0, plus the fact it is being multiplied by delta t. So, technically, even though theoretically it may not be right, but practically you can assume these values are almost tending to 0. That means, the last term and the second last term. So, if I highlight it, this is the values. These two terms I am basically ignoring. So, if I do that, you will find out the equation is the first terms which are here, and the second term is basically coming from the second differential of the x term, nothing to do with t. Because if you note, because delta x has a component which is an order of square root of delta t, hence it can be ignored. Now, suppose the rates which is mu, which we did consider that it is constant with respect to time if delta t is almost tending to 0, or we can also said that sigma is a constant if we consider it with respect to t where delta t is tending to 0. Then if we are able to expand that, then we had the simple equation where factor of time and x are not going to come. But if we consider the factors of time and space are going to come, the equation is this. So, if we bring here this as mu of s comma t, and this is sigma of s comma t, then the finding the equation and finding the Taylor series expansion may be tricky, even though it may give you better results, but that would not be worth the overall effort you are going to spend. So, now the final equation which we have, considering that a or mu, b or sigma are not dependent on where you are and not dependent on time, the final equation ignoring any second terms of delta t square root or delta t square root squares, the actual equation is this, which means the partial differential equation using the Taylor series expansion is given by these terms. So, now as epsilon we have considered is basically a standard normal deviate with 0 mean and 1 standard deviation, hence the mean value is 0, and if we consider the variance would also come out to be 1 as we already considered. So, it follows that if you find out the expected value of epsilon square delta t, it would come out to delta t, because the respect of these two assumptions which I have already noted down. The variance of delta t is proportional to delta t square and can be ignored, hence the final equation as we mentioned is this. This is with respect to x first differential, this is respect to t first differential, and this is respect to x, but the fact that higher terms of this can be ignored and higher terms of this can be ignored. This is the case where you are differentiating with x and then t, or t to x, and here you are differentiating twice with t. Now, if you take the limits, we obtain the final formula, which is this, which is basically the Ito's lemma. So, now what we need to do is that given the spot prices S, we are going to find out a derivative which is a function of the spot price depending on the values of mu and sigma. We can find out what is the actual price of that derivative. So, applications of Ito's lemma to a stock price process, stock's price and its process. The stock price, as we already know, is given by this drift term, volatility term. This is the Wiener's process. This is S is the spot price. Now, if we bring it in the picture for a function of Z, which is basically of S and T, not X and T. S is the spot price. The actual equation basically becomes this. So, now you will basically you will have the drift rate, you will have the volatility rate here, and you will basically have the square root terms of the volatility depending on what is the spot price. But remember one thing, the fact that we have assumed A and B are independent of X and T, or mu and sigma are independent of S and T, even though are logical to serve and solve, in practical sense they may not be true, in the sense that the assumptions we are taking as mu and sigma to be independent are not true. Now, if you consider the forward price of a stock for a contract maturing at time t is given by this, we already know. So, because it is an American one, and if we consider it is e to the power R f, which is risk free interest rate into t into S0. If you consider this g is a function of this, then if you solve it, the function becomes like this, which is the rate of change of g is now being given by two terms, which is the excess rate of that particular stock over the risk free interest rate. If you remember, we have considered that in some of the optimization problem, and the volatility rate. So, now it consists of two terms, excess rate over the risk free interest rate and the volatility rate. And what are the other factors? One would be the time difference, which is delta t or t, and one would be the simple Wiener process, which you assume underlying assumptions in the model. Now, if g is a logarithmic function, if you solve it, the overall function comes out to be this. Again, this is the average rate, but an average rate would now decrease by the term of sigma squared by 2, which sigma is basically the volatility. And in the same way, the second term, which is the white noise, continues to be remain as sigma. Now, consider that if we had the equation as given, the simple one, which was true, mu is the drift rate, sigma is the volatility or the white noise, and on the left hand side you have the rate of change, which is delta S into S divided by S. Hence, if you are able to solve it, it comes out to be this, where we assumed that the stock prices are log normally distributed. So, if it is log normally distributed, the prices are given by this, where the log of the spot price as of today would basically be a normal distribution with two parameters, which is the mean and the standard deviation. So, the standard deviation, the variance continues to be sigma square into t. T is the time difference from where you are and where you are trying to measure, and sigma square is the volatility per unit time, or volatility which is constant if delta t is very small. Delta t and this capital T are again different. Let me again mention. This is what we are considering, and the mean value would basically depend on the mean value as of now plus a constant term. And where is this term coming from? This was what we have considered in the last case, just the class case here, multiplied by again capital T is given by this formula. So, assumptions on the Black-Scholes. So, we have been able to at least get a feel that how the stock price is using the Ito's lemma, the Wiener process, the generalized Wiener process, and the assumptions we consider about the volatility and the drift rate. So, based on the fact, we have been able to simply derive and understand the Black-Scholes model, but let us first also try to analyze what are the important assumptions based on this model was developed. The assumptions are very simple. The stock pays no dividend during the option life. If you remember, we did consider this time and again that there is no dividend. That means the value of I0 or any independent payment which is being made and they are being calculated as of now would not be considered. Most companies pay dividends to their shareholders. A common way of adjusting the model for this situation is to subtract the discounted value of the future dividend from the stock price as of now, which is S0 minus I0, but we are not going to do that in the simple calculation of the Black-Scholes model. Second one is European excess terms are used, which means if you remember, the time to expiration for the European one was exactly fixed at time t is equal to capital T. Those are not American options. It says the European exercise terms dictates that the option can only be exercised on the expiration date. American exercise terms allows the option to be exercised at any time during that period of time before it expires. So, this limitation is not a major concern, but it can be solved accordingly. We will also consider markets are efficient, that means the demand and supply of the prices are such that it would basically be able to give the perfect information how the spot prices are being dictated. There is no commission charge, and also we will consider there are no taxes. That means, if you are selling and buying a particular option or a stock in the market, you are using the broker's help. We will consider that you are not either paying any amount to the broker for buying and selling this different type of stocks and option. And we will finally consider the interest rate remain constant, that means the mu value or the sigma value which you have constant will always continue to be constant with respect to time. This I had mentioned time and again when we were deriving it, and the returns are log normally distributed such that based on the fact that the deviation which you did for the using the Utro's lemma for the Black-Scholes model continues to hold true. So, finally, we wrap up this class, we will take another 2 minutes. The final equation for the Black-Scholes model would be given by this, where f is basically the corresponding the value of the forward contract which we are discussing, the capital A of the small f, which is dependent on risk free interest rate and the spot price and the differential equation which you already got. So, g was basically the function which was dependent on s and t, and based on that we found out, and mu was the rate of change of the function, and RF was the risk free interest rate. So, we are basically trying to find out with respect to how big or small the value or rate of the change of the function is with respect to RF. Based on it, we will try to invest into that derivative. So, S is the stock price, RF is the risk free interest rate, T is the time, and the volatility of the underlying asset is given, which is the actual stock we are trying to buy and sell. So, remember one thing, that RF is constant as mu and sigma are constant. So, method for calculation for the put and call option can be found out using any financial calculators which you have, and a good site for an example in the net can be found out here. So, we will continue our discussion with other models later on, and then come back and trying to explain that how the Black-Scholes model can be utilized in trying to find out the prices of the options based on the spots which are available. Thank you very much.